Picture this: two ancient humans, same species, same approximate age, standing next to each other somewhere along the migration route that carried humanity out of Africa and into the rest of the world tens of thousands of years ago. One of them has tight, densely coiled hair sitting close to their scalp, springing away from their head in a natural halo formation that looks like nature designed it deliberately. The other has straight hair lying flat against their skull, dark and smooth, hanging down past their ears. They are both fully human, both Homo sapiens, both carrying the same basic genetic architecture that defines our species. And yet there is this visible, immediate, obvious difference sitting right on top of their heads that any observer could notice from 50 meters away. Why? Why does one human have tightly coiled hair and the other have straight hair? Why does the person from equatorial Africa look so different in this specific feature from the person whose ancestors wandered into northeastern Asia 10,000 years earlier? Why did evolution, which is ruthlessly practical and completely indifferent to aesthetics, bother producing this diversity of hair texture at all? What was the point? Here is the thing. Hair texture is not random. It is not an accident. It is not a neutral variation that evolution happened to generate and then forgot about. Every major hair type that exists in any human population on Earth today exists because it was, at some point in our evolutionary history, genuinely useful in ways that affected survival and reproduction. The diversity of human hair textures is a map of where ancient humans went, what environments they lived in, what survival challenges those environments created, and how their bodies responded to those challenges across thousands of generations. Today we are going to read that map. We are going to start at the very beginning with the question of why ancient humans lost most of their body hair in the first place, and then we are going to trace the full story of how and why hair texture diversified as ancient humans spread across the planet. By the end of this video, every time you look at a head of hair, any head of hair including your own, you are going to see something different than you did before. Let's go. Before we can talk about why different hair textures evolved, we need to answer the question that sits underneath the entire conversation. Why do humans have hair on their heads at all? This sounds like a strange question until you think about it carefully. We are the only primate, the only one, wasp, that has a hairy head on an otherwise relatively hairless body. Every other primate has hair distributed relatively evenly across most of their body, with their head being part of that general coverage. We flipped that completely. We are almost entirely bald across our torsos, backs, and limbs while simultaneously maintaining a thick, dense, continuously growing patch of hair specifically on the top of our heads. That pattern is bizarre, and bizarre evolutionary patterns always have explanations. The story starts roughly 1.6 to 2 million years ago with Homo erectus, the ancient human ancestor that appears to be the first member of our genus to have substantially lost the dense body fur that earlier hominins possessed. The most widely supported explanation for this body hair loss is thermoregulation. When the ancestors of Homo erectus transitioned from living in the relatively shaded environments of forests and dense woodland into the more open, hotter, sun-exposed environments of the African savanna, they faced a serious and specific thermal challenge. Walking and running upright in hot, open environments under direct sunlight created an overheating problem that body fur made worse rather than better. Dense fur traps heat against the body. It prevents the evaporative cooling from sweat from working efficiently. In a cool or shaded environment, fur is valuable. It retains body heat. In a hot, open, sun-exposed environment during sustained physical activity, it becomes a liability. The solution that evolved over hundreds of thousands of years was a remarkable and in many ways unique mammalian adaptation. Ancient humans progressively lost their dense body fur while simultaneously massively increasing the density of eccrine sweat glands, the glands responsible for producing the cooling sweat that evaporates from skin surface. Humans have somewhere between 2 and 4 million eccrine glands distributed across our bodies, an extraordinary density compared to other primates who have eccrine glands only on their paw pads. We became essentially the sweatiest animal on Earth by a significant margin, and that radical sweating capacity, combined with bare skin to let it evaporate from, allowed ancient humans to cool themselves during sustained physical activity in hot environments with an efficiency that no other large mammal could match. But here's the problem that body hair loss immediately created. The top of the human head, once you are standing upright as a biped, becomes the surface most directly exposed to overhead solar radiation. The sun, which in equatorial Africa is more or less directly overhead for a significant portion of every day, is hitting the top of your skull at maximum intensity. And inside that skull is a brain that is extraordinarily sensitive to heat. The human brain is remarkable in many ways, but one of its less celebrated features is how thermally exceptionally fragile it is. Core brain temperature above approximately 40 degrees Celsius produces serious neurological damage. Above 42 degrees, it is quickly fatal. The brain cannot tolerate the kind of temperature extremes that other body tissues can manage. It needs to be kept cool with a precision that no other organ requires. An ancient human standing in direct equatorial sunlight with a bare skull would be absorbing solar radiation directly onto the bone that encases the brain. That is a direct thermal threat to the most important organ in the body. Body hair loss solved the overheating problem across most of the body but created a specific and serious new vulnerability at the top of the head. Scalp hair provided direct shielding of the top of the head from solar radiation, the site most exposed to the sun after bipedalism was established. The answer was to keep hair specifically on the head even as it disappeared elsewhere. The head needed a shade structure, and hair, maintained on the scalp as a permanent canopy over the skull, provided exactly that. This is why you have hair on your head and not on your back. Your back, when you are upright, doesn't face the sun directly at maximum angle. Your head does. The hair stayed where the thermal protection was needed, and was lost where it was becoming a cooling liability. Now we arrive at the specific question of why that head hair is curly in some populations and straight in others. And this is where the science becomes genuinely fascinating. Research published in the Proceedings of the National Academy of Sciences in 2023 provided some of the most rigorous experimental evidence to date for why tightly curled hair was the original hair texture of our species, and why it provided a specific and significant survival advantage in the environment where our species evolved. Researchers at Penn State University used a thermal mannequin, a head-shaped object heated to average human body temperature, and placed it in a climate-controlled chamber with different wigs. One straight, one moderately curly, one tightly curled. They then measured how much heat the mannequin absorbed from simulated solar radiation with each hair type. The results were unambiguous. All types of hair gave some protection from the sun, but tightly curled hair gave the best protection and minimized the need to sweat. A significant finding. The mechanism behind this is elegant. Unlike straight hair, curly hair doesn't lay flat on the head. The more curly the hair is, the farther off it is from the scalp, and the less heat reaches it. Tightly coiled hair creates a natural air gap between the hair mass and the scalp surface. That air gap acts as insulation. It slows the transfer of heat from the heated hair surface down to the skin and skull beneath. The hair absorbs the solar radiation, but the structural geometry of curly hair prevents that absorbed heat from reaching the scalp efficiently. Straight hair, by contrast, lies flat. It absorbs the same solar radiation, but transfers it directly to the scalp because there is minimal air gap between the hair and the skin. It provides some protection, better than no hair at all, but it is significantly less effective at keeping the scalp cool than tightly curled hair under direct overhead sun. For ancient humans living in equatorial Africa, running and walking in open savanna under intense overhead sunlight, hunting prey through the hottest hours using the persistence hunting strategy that depended on sustained physical activity. This thermal difference was not trivial. In a hypothetical sense, curly hair might have allowed ancient humans the ability to partake in longer, strenuous physical activity before needing a drink of fresh water. In an environment where water was a critical and often scarce resource, the ability to extend physical activity before reaching critical dehydration, because your brain was staying cooler and therefore your body wasn't burning through cooling resources as fast, was a direct survival advantage. Tightly coiled hair was not an aesthetic preference. It was a heat management system, a biological air conditioning unit built directly into the anatomy of every ancient human in equatorial Africa. The populations that had it could hunt longer, travel further, and function more effectively in the hottest conditions than populations without it. Now here is where the story gets more complex and more interesting, because the tightly coiled hair that was optimal for equatorial Africa became progressively less optimal, and in some conditions actively disadvantageous, as ancient humans began migrating away from the equator into cooler, less intensely sun-exposed environments. The migration out of Africa, which the genetic evidence places beginning roughly 60,000 to 70,000 years ago, carried ancient human populations northward and eastward into environments that were fundamentally different from the African savanna in their thermal profile. Europe, Northern Asia, and eventually the Americas presented ancient humans with environments where the thermal challenge was no longer primarily about staying cool under intense overhead sun. The challenge shifted toward staying warm, managing cold, and in some populations dealing with months of reduced UV radiation rather than excessive UV radiation. In these environments, the specific advantages of tightly coiled hair began to diminish. The overhead sun angle in higher latitudes is lower. Sunlight strikes at an angle rather than from directly overhead, reducing the thermal loading on the scalp. Temperatures are cooler, reducing the general overheating risk. The priority shifts from maximum heat rejection to maximum heat retention, which is a fundamentally different engineering requirement. At a later point in human evolution, curly hair may have lost its evolutionary advantage, and straight hair may have been favored by different types of genetic selection. As ancient human populations spent generations in cooler, less intensely irradiated environments, the selection pressure that had maintained tightly coiled hair began to relax. Genetic variants that produced straighter, flatter hair textures were no longer being actively selected against. In some environments, they may have been mildly advantageous. Straight hair lying flat against the skull retains slightly more heat in cold conditions than curly hair with its air gap, because that same air gap that provides cooling insulation in hot environments provides less thermal retention value in cold ones. Over thousands of generations in cold northern environments, ancient human populations shifted towards straighter hair textures, not through any single dramatic mutation, but through the gradual accumulation of genetic variants that produced flatter follicle shapes, less curved follicle geometry, and progressively straighter hair. Here is the biology of how hair texture is actually determined at the follicle level, because understanding the mechanism makes the evolutionary story more concrete. Hair curl is largely determined by the shape of its follicle. A hair follicle with a round cross-section typically produces straight hair. Conversely, oval-shaped follicles tend to yield curly hair, with a flatter oval shape resulting in tighter curls. The angle of emergence also contributes. A curved follicle causes hair to curl as it grows, while a vertical one produces straight hair. Beyond follicle geometry, the distribution of structural proteins within the hair shaft matters enormously. Disulfide bonds between keratin proteins influence hair texture. Curly hair generally exhibits a greater number of these bonds compared to straight hair, contributing to its coiled structure. What this means at the genetic level is that the transition from tightly coiled to wavy to straight hair across human populations involved changes in multiple genes affecting follicle shape, the angle at which the follicle sits in the skin, and the distribution of structural proteins within the growing hair shaft. Certain variations in the KAP cluster genes are present in African populations, but virtually absent elsewhere. Genes responsible for keratin structure that play a significant role in the final shape of an individual's hair. The genetic architecture of hair texture is not a simple one-gene system. It is a complex network of interacting genes, which is why the full spectrum from tightly coiled to dead straight exists, rather than just two discrete categories. The enormous variety of wavy textures, loose curls, tight curls, and everything in between represents different combinations of follicle shape variants across this genetic network, each combination producing a slightly different texture outcome. Here is a piece of the hair evolution story that almost never gets discussed in popular accounts, and it changes the picture significantly. The parasite argument, one of the less obvious but genuinely compelling theories about the evolution of human body hair loss, is that it was partly driven by the survival advantages of reducing the habitat available for ectoparasites, lice, ticks, and fleas, that lived in fur and transmitted disease between hosts. Dense body fur is, from a parasite's perspective, an excellent habitat. It provides cover, attachment points, and easy access to the skin and blood supply that parasites need. An ancient human with dense body fur was carrying a significantly larger potential parasite load than an ancient human with bare skin. Given that certain lice species transmit diseases including typhus, relapsing fever, and trench fever, diseases that could kill efficiently in a world without antibiotics, the survival advantage of reducing parasite habitat through hair loss was real and potentially significant. This parasite reduction theory complements rather than contradicts the thermoregulation theory. Both selection pressures, the need to stay cool during sustained activity and the need to reduce parasite load, would have been acting simultaneously, and both would have favored hair reduction across most of the body. The head is interesting in this context because it presents a partial exception. Scalp hair was maintained despite the parasite risk it carried, which tells us that the thermal protection benefit of scalp hair was significant enough to outweigh the parasite cost. The calculation was different for the scalp than for the back or the torso. Scalp hair survived because the brain inside the skull needed that shade canopy badly enough that even the parasite trade-off was worth it. This is evolution doing cost-benefit analysis in slow motion across hundreds of thousands of years. Every feature of human hair, the presence of scalp hair, the absence of dense body fur, the specific texture of that scalp hair, represents a solution to a specific survival problem that was weighed against competing costs and refined over geological timescales. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Let's talk about sexual selection, because the thermal protection story is compelling and well supported. But it is probably not the only force that shaped human hair diversity across different populations. Sexual selection, the evolutionary process by which traits that are preferred by potential mates become more common in a population over generations, has almost certainly played a role in the maintenance and diversification of human hair textures across different environments. The specific direction of sexual selection on hair texture in any given population would have been shaped by what was common, and therefore what was perceived as attractive in that specific cultural and geographical context. In a population where straight hair was universal because all ancestors had lived in high-latitude environments for thousands of years, straight hair would have been the beauty standard, not through any conscious cultural decision, but through the simple evolutionary mechanism that mates who look healthy and vigorous according to the population's established norms attract more reproductive success. A rare variant from the population norm might have faced mild disadvantage through mate preference, which would have reinforced the predominance of whatever texture was already common. This is one of the reasons why hair texture shows such strong geographical clustering even in the absence of strong ongoing selection pressure for thermal performance. Either environmental or sexual selective pressure began acting on hair after humans began dispersing out of Africa, helping shape the wide range of human hair types present today. Once a population had established a modal hair texture through environmental selection, sexual selection may have reinforced that texture by making it the local beauty standard, even after the original environmental pressure had diminished. Sexual selection for hair also operated on color, length, and thickness alongside texture. The remarkable diversity of human hair color, from jet black to blonde to red, covering a spectrum that no other primate approaches, reflects both the relaxation of selection for dark hair as UV radiation decreased in northern latitudes, and the action of sexual selection on whatever variants were locally common and attractive. Here is where this all connects back to something tangible about the ancient humans who lived this story in real time. Ancient humans migrating out of Africa were not making conscious decisions about their hair texture or its advantages. They were not thinking about follicle geometry or disulfide bonds or UV radiation physics. They were living, surviving, reproducing, and dying in environments that ruthlessly rewarded certain traits and quietly penalized others. The hair texture you are carrying right now on your own head is the end product of millions of years of that process operating on your specific ancestral lineage. If your ancestors spent their evolutionary history in equatorial Africa, the tightly coiled hair they maintained was a finely tuned thermal management system that helped them hunt in midday heat, protect a growing brain from solar radiation, and push the limits of endurance in conditions that would incapacitate most other animals. That hair is not just hair, it is a technological solution to one of the most serious physical challenges ancient humans faced. If your ancestors spent their evolutionary history in the cooler, lower UV environments of northern Asia or northern Europe, the straighter hair they developed reflects a different set of trade-offs, different thermal priorities, different UV exposure levels, different selection pressures that gradually shifted the genetic dial toward follicle shapes that produced flat-lying, heat-retaining hair. Every hair texture in the spectrum between these poles tells a story of a specific ancient human population navigating a specific environmental challenge at a specific point in their migration across the planet. The diversity of human hair is not random noise. It is a library, a physical archive of where ancient humans went and what they found when they got there, written in the shape of a follicle and the angle at which it sits in your scalp,